Hi everyone. Well, the last question actually is about the transfer product of linear maps, which you didn't see theoretically. But as far as I understand from your comments and Google documents, many of you also follow some online resources. Of course, be careful while following them, but for this type questions like transfer product of two matrices, we may easily get information. And when you see this topic in the future, actually, you will see a more accurate definition for the transfer product of matrices, because here we don't use any basis, any order, and etc. But at the moment, we only simply consider the definition of the transfer product in this way. So that means in this transfer product, we will have 4 block matrix, and in the first block is determined by the doubled of B, -2, -4, -2, 4, 0, 4, 2, 0, 2. And for the second block, we simply consider B as it is, because 1 times B gives it itself. And for the third block, we consider the zero matrix, 3 by 3 zero matrix, because when we multiply the each entries by 0, we get the 0. And for the final block, it's going to be minus B. So for the transfer product, actually we get 6 by 6 matrix. And for the last point, we have 2 diagonalizable matrices, and we know that A has eigenvector V with the eigenvalue lambda. Similarly, B has eigenvector W associated with the eigenvalue mu, and we only use the hint. And in the future, please think about why do we have this. So this means we have a vector which is determined by the transfer product, but we have another linear transformation determined by the A tensor B, and we want to evaluate this vector under this linear transformation. And by the hint, we know that actually this transformation behaves like in this way. So that means first you can compute the A of V, and similarly you may observe the image of W under B. And we also know that these values are the same as lambda V tensor mu W. And for the tensor product, we may remove the scalars on the left side, and by the definition of the eigenvector and eigenvalue, we see that actually this vector, which is determined by the tensor of V and W, will be an eigenvector for this tensor product with the eigenvalue lambda mu. And again, this is all what I want to say for this question, but in the future, when you see this topic again, you are going to see this. Please be careful while taking the definition. Why can we take this definition as it is? It's a bit artificial at the moment. Yes, and the second thing in the future you should think about, why do we have this equality? In this case, basis will be important. Okay, thanks for your attention. And just last comment, for only this homework, I just want to note that To match with the script and the homework can be really challenging, so no worries about it. Take care. Thanks for your effort in this exercise class. You really work hard and I really appreciate that. Okay, wash your hands, take care, and bye-bye.